You have watched the video where we used so that we could represent in 3D vector u as u1i plus u2j plus u3k, and a vector v as v1i plus v2j plus v3k. And of course, you can then do u plus v, where you have u1 plus v1i plus u2 plus v2j plus v2 plus u3 plus v3k. And the same if we want to do subtraction, then it's a minus here, and minus here instead of plus. So those are simple operations that you can do with vectors. So what we will discuss now and also introduce in one of the video is how do you do the product of two vectors. So the concept of multiplication of vectors translates into a useful tool for many engineering applications with two different products of vectors, what we call the scalar product or the dot product, and a vector product. Scalar product, also called the dot product of the two vectors u and v. This is the multiplication of elements by elements. So the sum of the product of the elements of the two vectors. And I have shown in the video a demonstration how you get the value of u dot v, which is then u1 v1 plus u2 v2 plus u3 v3 as the definition of the dot product. In other ways, this can also be represented as the modulus of u times the modulus of v times the cosine of theta, and theta being the angle between v and u. So dot product is the same as scalar product. That means if you do the product, what you get is a scalar because you are just adding the product of the vector, and this is not a vector, it becomes a scalar. But it's called either a scalar product or a dot product. And of course, knowing this relation, if you want to find the angle between two, that will be u times v divided by the modulus of both vector, and theta will then be r cosine or cosine minus 1 of uv divided by u dot v. This is quite a simple definition. Suppose that you have given two vectors a 1 2 3, and then another vector b 2 0 4, and you are asked to find the angle between vectors a and b. So we have a dot b, which is given as the modulus of a times the modulus of b times the cosine of theta. And of course, this is equal to the product or the sum of the products a1 b1 plus a2 b2 plus a3 b3. That means we can actually say if we take A times B, that should be equal to 1 times 2, this one, plus 2 times 0 plus 3 times 4. This is equal to 14. So you take the first element times the first element, and the second element times the second element, and the third element times the third element to get the scalar product. And using this relation here, we also need to know the value of the modulus of A, and this is given as the square root of A1 square plus A2 square plus A3 square. In this case, what we have is 1 squared plus 2 squared plus 3 squared. This is equal to 9 plus 4 plus 1, which is the square root of 14. We should also know the scalar, the modulus of B, which is then given as 2 squared plus 0 squared plus 4 squared, which is 16 plus 4, which is the square root of 20. And using this formula here, we can then say theta will be equal to cosine minus 1. This is cosine minus 1. AB is equal to 14 divided by the square root of 14 times the square root of 20, because they represent, each of them represent the modulus of A and modulus of B. And of course, you can express this one as cosine of minus 1, and then which will be 14 divided by square root of 14. That will be the square root of 14 divided by square root of 20. That means cosine minus 1 of square root of 7 divided by 10. And then you can use your calculator to find the value of theta. And the other product, when using a vectors, is called the vector product. Of course, a scalar product, you get a scalar after the product. A vector product, you get a vector after doing the product. That's in a simple way. Geometrically, the vector product between two vectors A and B is a vector n that is perpendicular to both vectors. And again, in the video, I've made a proof how to get the expression of A cross B, the vector product. And let's here give the final answer. The vector product of A and B will be the product of the modulus of each of them, sinus of theta, which is the angle between the two vectors, and then the normal vector, which provides a vector that is orthogonal or perpendicular to A and B. So this concept finds application in many engineering concepts, such as when you look at the moment of a force. The moment of a force is actually provided as the cross product of the force and the displacement or direction of the force. As you will see, so this is A dot B, which is A B cosine of theta. This is a scalar, and this is, because of the normal vector, a vector. There are properties that are associated with the concept of scalar and vector product. For example, while you have a commutative law of the dot product, that means u dot v is equal to v dot u. If you take A cross B, that will be minus B cross A. What it means is that if you interchange the position, then the resulting vector will be a vector that is opposite to the normal vector. And of course, that vector will also be perpendicular to both A and B. And the vector is an object that has a magnitude and a direction. So how do you compute the value of A cross B? You can either remember the formula as given in the book or in the video as well, or you can use a matrix form. In that case, you provide I, J, and K, A1, A2, and A3, B1, B2, and B3. Instead of remembering the formula, if you place your vectors in this structure, it becomes quite easy to compute the vector product. What you do, if you want to look at the element of I, you hide this line and this line here. And then you multiply this way minus this way. So what you get as the component of I will be A2, P3 minus A3, B2, I. So in the same way, if you want to look at the component of J, what you get is J, K, A1, A2, and then we hide the line of J, and then you do the multiplication between the remaining elements. In that case, the component of J will be minus, because it's the second element, A1 B3 minus A3 B1J. And if you apply the same technique with the K, and then when we hide the line of K's, what we have left is this one and this one. That means K will be A1 B1 minus A2 B, sorry, A1 B2 minus A2 B1 K. So that A cross B. So the formula will be given as A2 B3 minus A3 B2I minus A1 B3 minus B1 A3J plus A1 B2 minus A2 B1 K. This is how you compute the vector product between two vectors. You can either remember this one or derive it yourself. If we take an example, so given two vectors A, 2, 1, 0, and B equal to to 2, minus 1, and 1, you are asked to evaluate A times A cross B. We use our disposition AJK 2, 1, 0, 2, minus 1, and 1. So now you have the option to look at the formula and apply it, or then if we do the first one, let's hide for I. What we have is this box here. That will be 1 times 1, which is 1, minus 0, which is 1I, minus, if we now look at J, what we have is the box here and here. That will be 2 times 1, which is 2, 2 times 0, and 0, J, plus, if we now have the K, we have this box here. That will be 2 times minus 1, that will be minus 2, minus 2 times 1, that will be 2K, and then our vector product is given as I minus 2J minus 4K, or just in parentheses, 1 minus 2 minus 4. So, in a plane, what we learned was that a line is determined by a point and a number, giving the slope of the line, while in space, a line is determined by a point and a vector that is giving the direction of the lines. If we are in space, Suppose that we have a line passing through point PO with coordinates XO, YO, and ZO. So a line L passing through that point, and which is given with a direction that means parallel to a vector V, and V is given as V1I plus V2J plus V3K. So the set of all points P given X, Y, and Z, for which the vector PO and P is parallel to the vector V, we can express the ratio between the vector P0P will be a scalar times the vector V, because those vectors are parallel, same directions. It's just the main difference will be the magnitude. In this case, the magnitude is governed by the position of P, and then we allow the distance between P and P0 to vary. So the equation in the line will then be given knowing 2 points, the vector with the tail P0 and head P can be written as X minus X0I plus Y minus Y0J plus Z minus Z0K, and this one should be equal to T, and then we have vector V1I plus V2J plus V3K. This can be expanded by multiplying using the parentheses. That means we get Xi plus Yj so the P0 to P is the vector that is made of P0 and P, which is parallel to V. And that vector will depend, of course, on the position of P, because P is a varying point on the line, and that is why it is written as TV. Plus ZK, and then, so V is the vector that provides the direction of the line. That means the line is parallel to V. And T is a scalar. Why do we have a scalar here? If you remember, two vectors are equal to each other when they have the same magnitude and then they have the same direction. POP will have the same direction as V. That means they are parallel. And when we vary the position of P, we also vary the magnitude of the vector P0P. That is why the magnitude of the vector P0P can be written as a scalar multiplied by V. To indicate that they are parallel, that means they have the same direction, but the difference is in the magnitude. And then we can send XO on the other side, as well as YO. That will be plus XOY plus YOJ plus zk, and then plus, I will have to keep this one as it is. This would be here. For the two vectors to be equal to each other, that means the component of I should be equal to the component of I on the other side. In this case, we also have, if I develop the second point, that will be T V1I plus T V2J plus T V3K. And therefore, the parameter of the line is just provided as x given x0 plus vt1, y equal to y0 v2, and z equal to z0 plus tv3. This is the three scalar equations involving the parameter t. And if we assume that we have a position vector between the position vector for the points P0 and a position vector for the point P, which is R, the expression of the line is provided as RT equal to R0 plus TV, which is a vector equation for a line through P0 parallel to the vector V. So this is the vector equation for the line L through P0 and parallel to the vector V. So if you are asked to find the parametric equation for the line through a point P0 minus 2, 0, 4, parallel to the vector V, given as 2i plus 4j minus 2k. Going back here, we see that knowing the P0 and then the direction, our line can easily be expressed, or the parametric equation can easily be expressed as x equal to x0 plus tv1. This is minus 2 plus 2t. Y will be y0 plus tv2. This will be 0 plus 4t equal to 4t. Z will be z0 plus tv3. That will then be 4 minus 2t. And that's it. This is the parametric equations of our line. We can then also define the points, the distance of a point to a line. If we have a line passing through P and then a direction V, and we have a point S, the distance between that point should be normal to the line, which is here the corresponding vector, and then sinus of theta. So what you have to remember is there is not much demonstration for this formula, is that you can compute the distance between a point and a line by taking one point in the line and then looking at the vector to the point that is outside the line. You take the normal vector to the direction, and then you divide it by v to obtain the unit vector of v. But what we are interested here is just the direction of v. That is why we have the modulus of v divided. This is the distance between a point and a line. In the same way we define a line, we can also define the equation for a plane in space. A plane is determined by knowing a point on the plan, a point P, PO, the same as before, XO, YO, ZO, and the tilt of the plane or the orientation. And this can be defined by the vector that is perpendicular or normal to the plane, vector n. And of course, this vector is perpendicular to all the vectors lying on the plane. So for any other vector that we define with P0, P, X0, Y0, Z0, X, Y, Z, this normal vector will be perpendicular to all the vectors lying in the plane. And therefore, by assuming that the normal vector is A1 plus BJ plus CK, and knowing that our normal vector is perpendicular to any vector P0P, this can be expressed by the definition of the dot product. And then when two vectors are orthogonal or perpendicular to each other, the dot product equals. And therefore, we can just write here AI plus BJ plus CK dot. The vector that is made of P0 and P will be the difference in the component, I, plus Y minus Y0I, plus Z minus Z0K, and then this will be equal to 0. So the plane consists of points satisfying the equation IX minus X0 plus B Y minus Y0 plus C Z minus Z0 equal to 0. So I think I will let you try to go through this in the slides, and then when we meet again, we then take the exercises and tutorials that are related to the concept of line in space and dot products and vectors in general. And I've made actually a quite long tutorial that will give you a very nice idea on how different problems can be formulated and resolved using vectors.